Okay, now the opponent challenging the reporter for the problem.其实他们要先挑人吗？还是说他们先确认举吧？
对，先挑3个。对。
We would like to challenge problem 7 ruler canal. Cannon.
Wait a sec. Okay, I'm going to start my report. I'm just turning from Team Laplacian. I'm going to report number 7, ruler cannon. And the problem statement is 2 rulers are tightly held against each other. A round projectile is inserted between them close to one of their ends. When extra force is inserted on the surface of the rulers, the projectile is ejected at a high speed. Investigate this effect and the parameters that affect ejection speed. And our key question is the interaction between the ruler system and the projectile, and also the ejection condition. And for that is the parameters affect ejection speed. This is my layout, and our setup is this is a video, and we use a plan to fix the left point, and the projectile is attached here, and we use a spring to insert it extra force, and you can see this is a force application point, and this is another experiment graph. And this is set up. Within the parameters can be the material of the ruler, and the length of a ruler, the diameter of the projectile, the force application point, distance, the fixed point, and this is D, and friction coefficient between ball and the ruler. And for response parameters, the obvious parameters can be the velocity of the ball, and we can calculate the kinetic energy and the shape of a ruler right before the projectile is ejected. And there are some important physical quantities. This is our report mainly about the bending potential energy of the ruler, and the energy transformation ratio to the kinetic energy of the ball. Okay. So for the observation, we can see the ejection condition is we use spring to we compress the spring, and when the ball is about to eject it, the tangent line is tangent line of the end point is tangent C, and that is a constant. This is because okay. This is because if we define these quantities, and we can use Newtonian law to find that the ejection condition is tangent theta is greater than mu, and before ejection, the ball will slip to the end of the ruler because it wants to get the minimum theta. For like this, I'm going to the x-axis is the time. This is the time, and this is a velocity. No, this is the displacement. This is an xt graph, and we see that the ball will slip to the end of the ruler, and the ruler accelerating at a high speed. Then it will go to a horizontal motion, horizontal projection motion. And for a theoretical view, we define 3 ejection stages. The first is the static stage. It is storing ruler's potential energy, V ruler. And second is the slipping stage. It transforms energy to the ball's kinetic energy, which is the accelerating stage. And for the last is the separated stage. Because it is separate from the ruler, it starts to do horizontal projectile motion. And for the ejection condition, we can calculate the tangent slope. We calculate many tangent slopes to find that the tangent slope is about to 0.109, and we have to find the friction coefficient to find our theory, if our theory is right. So we use 3 balls and we attach them together such that it won't roll it will only slip. So we can use this angle to find the friction coefficient of mu, which is mu, is going to be 0.113, and that is close, and that means our theory is right. And next is a ruler shape. For why we are going to solve the ruler shape? It is because we have to find the potential energy, and we know the potential energy. We are going to know the physical mechanism of this. So for a ruler shape, we can use Euler-Bernoulli beam theorem, and which is like this. For static states, it won't have a p term. It is EI for derivative of W is equals to Q, and Q is the force per length, and E is the Young's modulus. This has a displacement. This is point to E, and we can see a next graph by Euler-Bernoulli beam theorem. We first add the frame, and this is x-axis, and this is u. We are going to make a coordinate of the coordinate of this, and this is u, and we can apply that theory, and this is differential equation, and we have 4 boundary conditions, and we can use math to find that u is going to be this, and we can see that this is a polynomial, and 3-degree polynomial, and this is actually a 3-degree polynomial on the left side and the right side, and for the middle is the 4-degree polynomial, and this is the calculation, and we can use this to solve the force, because N is equals to that. That is just a symbol, and we can solve the force, minimum force of ejection, and we can fit the ruler shape. We regress the line, and we can use curvature formula to find this. And now we can calculate the potential energy. So we apply force at different spots, and the bending energy can be calculated as this formula. And because the ruler and the ball do inelastic collision, so the energy transformation ratio is going to be a constant. So we first find the velocity. This is velocity. This is a force application point. We find the graph of this, and we can calculate the kinetic energy. And for the kinetic energy, it is like this line. And for the bending energy, this is like this line. And the energy ratio is about 0.07223. And for a conclusion, the ejection condition is when the tangent slope match the friction coefficient. And we use different force application points to investigate the quantities in this physics system. And and we find the equation of ruler, and we find the minimum force eject the ball. And for most important thing is we know the physical magnitude. That is because we know the potential energy, and we calculate the ratio. And we can solve the equation of the ruler. So we know whole thing of this structure. So we can solve everything, and the transformation ratio is constant. Okay. Thank you.
Now for the question of the opponent.
So I want to ask about the page 13. And by constant, do you mean that the angle theta is constant at given parameters? Because as in the presentation you said constant theta. So constant under what condition?
This is the constant of the condition is the this we can see the variation is about the geometric interpolation. So this is geometric sign. So this constant is for a geometric.
So it's generally means constant.
That is related to mu. If the mu is a constant, then tangent theta is going to be a constant.
Okay, so the angle theta is constant at given mu.
Yes.
Okay, so can you go to page 19? And I want to ask about is the line here x-axis? X-axis.
We made this x-axis, and this is a u.
Oh, so this is the magnitude of u x, right?
Yes.
Okay. And can we go to page 21? And I wonder what you mean by this symbol of n. So what is n exactly?
Oh, n is a symbol we solved in the ruler shape. Everything we know is in this ruler shape. So
OK， 开始。
explain the process question here. 更多想留到大家，就只是想要讲我只想来
And maybe we can hold. Okay, should we start? Okay.
Start.
Okay, we start.
Okay. Hello everyone. I'm from the team Banana, and we're talking about the problem 7 ruler cannon. And let's get a quick outline of this problem. And the key points we're discussing about is the interaction between the ruler system and the projectile. The ejection condition where the ball is at the critical stage and the next second it becomes fly off, and the parameters that might affect the ejection speed. So in theory, the reporters use a Euler-Bernoulli beam theory to explain the movement of this ball while counting the rulers. And at experiment, they calculate the mu of between the ruler and the projectile to get a friction coefficient, and they calculate the bend of a ruler for theoretical models. And by conclusion, they said that the ejection happens when the tangent beta is greater or equals mu s, which means friction coefficient at this point. And the equation of the minimum force applied on the ruler to let the ejection occur. And they also mentioned that the transformation of energy between the potential energy of the system to the ball itself isn't elastic and is in reality an elastic coefficient. And the energy ratio throughout this process is constant. And indeed, they get the theory and experiment results match, which is good. So some advantages of this report is that it's simple to follow, and they get a simple approach to this problem and make some really nice results overall. And so the things I want to discuss in this theory is that one is about the value of mu overall, and about standard state, which the reporter stated in this report. And that's all. Okay. So should we move on to this? Okay. So the first question I want to ask is by the state, how do you define the standard state in this experiment?
I didn't define a standard state.
Yes, but throughout this presentation, you said that some values are fixed and it remains constant, but sometimes the constant is fixed under a certain state. So what is that state exactly? What is the state that you first do the experiment and measure out all the parameters?
Do you mean my experiment?
Yes, I was just wondering, like, when is the first time you did your experiment? What's the L of the ruler? The place that you applied the force, and how much did you apply? And when did the ball fall off? When did the ball eject out? And what is the speed exactly at this fixed state? So I want to talk about what's the fixed state of your report.
Fixed state of
yes.
So my experiment is like this, and we are going to place different force application point and to eject the ball. and then there are some parameters. For the length of a ruler, that is 11.8 centimeters, and for the diameter of the projectile, that is 1 centimeter. Is that what you want?
Yes, that's what I want. So, what exactly is E actually? I'm wondering more about the E.
D is a variable, and you can see
Okay.
in this graph. This, we choose different D to do the experiment.
Okay.
So this is a variable.
Okay, thank you. So, I want to talk about just. Can you go back to page 21 where we left off? So, can you explain to me what is N from what you read off, because the timer stopped.
Okay, so for N is a shorthand. This is because the difficulty of the differential equation. So we can see this. We can start from this. This is our differential equation, and this is a boundary condition. And for some math, we can find that this is a main equation of u of x, and N is just a shorthand because N repeat many times. So this is just a shorthand, and we can solve this N, and we can find the minimum force of ejection.
Okay, thank you. So, can you turn to page 24? Why do you, can you prove that the energy transformation ratio is constant at any given parameter?
This is by the experiment. We do an experiment. We compress the spring and let the ball go away. And for the most important is the we know the ejection condition and the potential energy. And for the ratio, we use experiment to prove that.
To prove that the mu eta remains constant throughout any given parameters, right?
Yes.
Okay, thank you. So, can you go back to the introduction of this problem?
Yeah.
Yes. And what do you think are the parameters that might affect the ejection speed?
Okay. So for our main idea, it is the from we can go from the ejection condition, and I'm going to use a backboard. And also, and we can know the curvature. And then we can find the potential energy. And we can find the kinetic energy. So for your question, you mean what changed this? I'm going to investigate the parameters. So for this transformation, there might be a parameters that the energy ratio. And for the second is what caused the curvature change. That is because some material properties, like Young's model, I, and so that is all the material property.
Sorry to interrupt, but what is I exactly? Because you mentioned that
that is a property about the ruler shape.
Yes.
For this ruler shape, we can find that I is and B is this and H is this. So that's a geometry. And But for recursion, this is first and second, third, and we can find more. If I can change the slide.
Sorry, may I add something? So did you consider the properties of this ball? For example, you said that a projectile is held between two rulers, but have you considered the projectile not a ball? Have you considered it a barrel or maybe a bigger ball?
Oh,
Just
I think you give a good point because the problem statement is about a round projectile, so your statement is also right.
Yes.
This can be a bottle.
Barrel.
Yes.
Yes. So what do you think will be different if I change this into a barrel with the same diameter?
So for a round projectile, it has a property like this, and we look this side. This is round. So we can use our formula of ejection condition. So what change the ejection condition? That is because mu. So mu change the ejection condition. So the friction coefficient between the ruler and the projectile is parameter.
Okay, so now for some question, not for the question. So you mentioned that tangent theta has to be greater or equals to mu in this case for the force eject, right?
Yes.
So you simply assume that mu remains constant during this whole process, did you?
Yes.
So why is that? Because it is sometimes inappropriate to assume that mu is always constant for different force applied to the ruler.
Oh, so you mean the force between the tangent force this is not a straight line?
Is that
I think you mean it. So we take the approximate of this, and our main idea is we use this formula. So this is a constant.
So you use linear approximation to approximate the relationship between f and n, and you assume that they are proportional.
For most material, that is the mu is always constant.
I'm sorry, but I'm not talking about the material that affects the mu. I'm talking about the mu changes due to the n applied onto the ruler. Even if it's the same material, the mu might change if the n varies.
This is a maximum. This is a maximum static friction, right?
Yes.
And for the ball, for this n is very small. That will be a straight line.
Oh, so n is very small.
Not for the whole scale. Yes.
Relatively small, right? So how will you control your experiments so that when you apply n to the rulers that it remains the difference remains so small that it's negligible.
Oh, so you have to look at experiment. So if my my theorem that is zero, that is this and this, so it fits well, right?
Yeah.
So it is right.
Okay. Let's move on to the next one. Okay, can you turn to page 27? Oh, so this is the point that you're talking about. You use an approximation to work out the constant eta by I don't know, average.
I don't think this is a different thing because you talk about F. This mu is not constant. You are saying that, but I think that is a constant.
Okay, time's up. Okay, let's move on the summarize.
Summary. We talked about first. We talked about what is a standard state at given parameters and what is the standard state of the experiment. And then we talked about the problem that mu might not be a constant for given material, for different materials or with different and applied onto the ruler, and how to maintain that change relatively small so we can ignore that deviation from the field. And the second, we talked about the eta, which is the energy transformation ratio between the between the potential energy of the system to the kinetic energy of the ball. And I think that we could have worked out some some parameters that symbolize this ratio.
Okay,
That
time's up.
using
Okay, the reviewer takes the floor.
Okay, so the question for both the reporter and the opponent. So what is the main source of the energy?
The main source of the energy is because of the inserted force on the surface of the ruler.
So, and for the opponent?
Sorry, can you repeat your
The main source of the energy.
main source of the energy? I think I did agree with the reporter is that hence the force applied onto the ruler did do work to the projectile and that it eject out.
Okay, thank you. So have you considered the elastic energy as well?
No.
No. So you have talked about the Euler Bernoulli feature and you have no consideration of elastic energy.
Your elastic energy is the bending energy.
Yes, depending.
Oh yes, we are all talking about bending energy.
So for the opponent, is the work caused by the external force or the bending energy?
The external force might cause the bending energy, might do work to the ruler that it bends. So the rulers contains bending energy because the force applied onto the ruler.
Okay, do you think it is the same?
I think it's relational, but you can't say that it's the same because some work are provided by onto the ball.
Do you have a defense for that? Do you have a defense for what the opponent said?
Can you say that again?
He says that it is relational, but they are not actually the same. Do you agree with the opponent?
What is the same?
The bending energy and the external force work.
No.
Okay, so they are not the same. So in page 13, do you think that the force applied at the point right here will be the same in throughout the phenomenon?
The force applied onto
Because from this picture, yes,
do you mean the point where we apply the force?
yes.
I think it did change because there can be different work done when we fix the F on the ruler and we press it on different points of this ruler. Yeah.
So is the angle of the force and the point of the applied force the same in the?
You mean this angle?
Yes.
Listen.
Meaning the force applied angle and the place of the force will be the same.
You can point this.
Yes, the force applied here and the angle of the force. Is it the same? Yes or no?
I don't understand your question, but for this tangent line, the slope is the same.
Okay. Do you think that this spring, the two springs are the identical springs?
Identical?
Identical because the two springs are different. And for the opponent, do you think the springs will be identical? And if the force is different, will it cause rotation?
The spring will be identical.
Yes.
Do you mean the rulers?
Yes, we have to test that.
Okay, so will it cause rotation?
Okay,
No.
time's up.
Thank you.
Okay, time's up.
Okay, so I am the reviewer from the laboratories team, and then we review on problem number 7, the ruler cannon. So this is the problem statement. I think the essence of the problem statement, the most important part, is the parameters that affect the ejection speed, which the reporter has not really talked about, and the opponent hasn't really pointed out the inconsistency. So this is my outline. So the pros of the reporter is that their key questions are clear, and they have a clear video and energy calculation. And the stage definition of the ejection process is pretty clear. And they use Euler Bernoulli beam theory to explain the bending of the ruler. Well, the cons is that the spring might not be identical in the experiment. And they calculated the tangent theta. However, they missed the use of integral. They can calculate the work from the external force with the theta from the initial to the ejection. And they have no proof that there is no rotation in the whole process, as I don't really see any good videos in their report. And they have no comparison with the theory and the experiment. They also have no explanation on why they can assume the process is inelastic. Also, the energy conversion discussion is unclear. The lack of discussion with relevant parameters, and they have very bad time control and a lack of experiment. The shape is also relevant, and they have no explanation on the ejection speed. And the pros of the opponent is that they have a very clear presentation. However, they do not ask enough short questions in the part for clarification, and they do not point out the reporter's inconsistency with the problem statement. And they lack the time management, and the discussion is not deep enough. So the first question is the coefficient constant, which they answer as the geometric, and the angle was stay constant. However, I think the angle over time, the function of the angle over time, is very important in the ejection, and it can be used to integrate the energy. And they asked the line of the ruler shaped x-axis, and the answer is the mu x is the magnitude. And I think that the reporter could have been more clear in the report. And the discussion is the standard state definition, and they have clarified the d as this number. And I think that in the graphs they should use force instead of the d. And they have clarification on the n, which the opponent says that, which the reporter says that it calculates the minimum force. And I think that this should be asked in the short questions. And this is the parameters of, they ask the parameters of the ejection speed, which they have explained clearly in the flow chart of the ejection to conversion from potential energy to kinetic energy. Well, I think that this assumes that elastic energy is the main cause, and neglects the work applied by external force. And they have clarified on what is I. I also think that this should be asked in the short questions instead of the discussion. Okay, so this is the other discussions with the properties of the ball, and what will be different if it's a different ball. And however, I think the reporter should have more experiments on this and could explain the slipstick phenomenon better. And this is, and I asked how to control the experiment, and I think that it is fit will, so it is right. However, I think that this is only one variable, and it cannot explain the whole process. So this is my questions, which I think that if the spring is not not identical, the reporter and the opponent both think it's identical. However, if it's not identical, the two sides of the force will be different. And then rotation might be caused due to a different force applied. And the main source of energy, they think it is the inserted force from the ruler, and the opponent agrees. However, they convert it into elastic energy, which I suspect that it calculates the same energy twice. So then the reporter says the bending energy, and the opponent says the external force does work to transform into elastic energy. Thank you.
For a concluding remark, and our own contribution, we have calculated the ejection condition, and we define 3 stages of the ejection, solving an equation of a ruler, calculate the potential energy, and the energy ratio is constant, and the experiment of different force application point, and the theory of the minimum force, and clearly physics concept. And for a concluding remark, tangent theta is due to the mu, and for a verification, and we have to do a verification, that is by the experiment. And for the energy, the bending of the ruler causes the bending, the potential bending energy, and transform ratio to the kinetic energy. And when the tangent theta is greater than mu, and it will shoot. And by experiment, it will provide a boundary condition to make the ball to shoot. And for review, the speed can be calculated by the kinetic energy. So we know the kinetic energy, then we know the velocity. So for a problem, we know the problem is about, because we calculate the velocity. Okay. Thank you.
So, any question from the jury?
So may I know of your opinion if I change the ruler surface and the ball surface, which means I change the friction coefficient, do you think the result will be the same?
No, because if the surface and the ball is changed, the friction coefficient is changed. So the ejection condition is changed.
Well, I think the friction coefficient will change, and it will change the whole energy of the process when the ball is getting out of the ruler, and change the slip signal.
I think that different conditions of mu might cause the energy done on the ball be changed, and overall just different ejection speed and different ejection conditions.
I want to follow the question. According to your model, when you change the material of the ruler and the ball, and which parameter will be changed in your model?
Okay, so in our model, our variable is the D, which is the force application point, and the material and the ball is not changed.
How about the changing rate? Transfer rate?
Transformation.
Yeah.
Transformation ratio is not changed.
According to your opinion, do you agree the transformation rate is a constant, because you say the experiment value and are very close to your theory calculation, and how much close to the between the two value is close enough, and then you can decide its video model? Because I think 0.1 or something.
I think this is okay.
This is okay. Do you agree? Why?
Well, because I think that for first, they calculate the energy converter rate, right? But they have no consideration of the work caused by the external force, and only calculate like the bending energy. which I think the work caused by the force is pretty important in this phenomenon.
I think that sorry, what's the question? I think I forgot.
Do you agree that the transformation rate is constant according to their data?
I think that we should define what is small enough for it to be negligible, and I think the argument between the why mu does mu remain constant in at different given, and it's not as well clarified because they said that it should remain at a relatively small range, and that small range is also not determined. So it might not be clear why should the eta be constant at this state because we haven't defined what mu is yet.
Any others?
Using the friction coefficient to describe the energy that we transfer. But the case is in the bending ruler, the direction of the force is changing, and the surface of the friction will change. So do you still think tangent theta equal to mu x can explain the phenomenon?
Yes, because this is a geometric. This is because this is n, this at 2 n, and this is a f. So I think if the mu is constant, then tangent theta is constant.
The theta between the applying force versus the surface of the friction force is the theta is equal to the pushing force.
Because this is for the maximum, and so we can solve this by Newton and
What direction is the pushing force?
this is, and this is.
What's the yellow force? What's the force in yellow?
The force is in yellow is the maximum friction. Maximum friction. So we can solve this by we have a theta. And that's close to. This is the ejection condition.
Because to the agree with theory.
The theory of what is that?
The friction force condition is important.
I do think that the coefficient of friction is an important variable in this period.
I think that kinetic friction is more important since the ball is moving. However, it also has a rotation, and they don't really have a good explanation on it.
I can solve it because if I know this theta, then this is theta, and for this line the force is n. So we have tangent. That is the result. By the
The issue is the ball don't have to follow the surface of the ruler. The ball is have to get out of the its orientation. In the inclined state, your ball is going in the same direction as the surface. But in this case, it's going this way. They're not following the surface. So we don't need to overcome the direction, the coefficient of the friction. Because they're getting out this way, you are creating this force.
I think if this is a curved line, and the ball is here, and the friction force is this direction. So
I mean, you get out in this direction. The ball is get out from the position.
the tangent, yes, tangent.
You never mind.
Okay. So okay, the score for the reporter. Five, 7, 6, 6, 4. And the score for the opponent. 5, 6, 7, 6, 6. And for the reviewer, 7, 7, 8, 8, 7. Okay, we have 15 minutes for a rest.